Since the end of the Second World War, the United States Navy, arguably the most technologically advanced maritime force in human history, has seen 20 of its warships suffer severe, mission-ending structural damage during combat operations. If you were to analyze the ballistics, you might assume these multi-billion-dollar vessels were struck by hypersonic anti-ship missiles, laser-guided munitions, or stealth torpedoes. But the engineering reality is far more sobering. Out of those 20 incidents of catastrophic hull failure, exactly 15 were caused by one of the most primitive, unglamorous mechanical devices still in active deployment, the naval sea mine. Let us analyze the raw mechanical economics of this kinetic exchange. An Arleigh Burke-class destroyer, or a Ticonderoga-class cruiser, represents a financial investment of roughly $2 billion. It is a floating fortress equipped with Aegis combat systems, phased array radars, and automated point defense Gatling guns, capable of tracking hundreds of airborne targets simultaneously. Yet, this pinnacle of naval architecture can be completely immobilized by a submerged iron sphere packed with high explosives that costs anywhere from a few $1,000s down to a mere $50 to manufacture. This is not just a tactical weapon. It is the ultimate expression of asymmetric warfare. It is a mathematical equation where the denominator of defensive cost exponentially outweighs the numerator of offensive production. For every $50 spent on casting an iron shell and filling it with ammonium nitrate, a modern navy must spend millions of dollars, deploy specialized sonar arrays, and risk highly trained clearance divers just to safely detonate a single unit. Geographically, this equation reaches its absolute extreme at one specific maritime choke point. We are looking at a narrow corridor of water, where approximately 20% of the global liquid hydrocarbon supply, the very lifeblood of the modern industrial economy, transits every single day. In this highly congested shipping lane, the strategic objective is not to engage in a symmetric fleet-on-fleet naval battle. Instead, local forces have systematically stockpiled an estimated 6,000 to 8,000 maritime explosive devices. This is not a conventional arsenal. It is a distributed, decentralized network of kinetic energy waiting to be unleashed. By deploying even a tiny fraction of this inventory, the defending force does not actually need to sink a hostile warship to achieve victory. They only need to trigger a single confirmed detonation against a commercial hull. The moment a kinetic strike is verified, the global maritime insurance market reacts with absolute mathematical ruthlessness. War risk insurance premiums for massive crude oil tankers instantly spike by 400 to 500%. Almost overnight, commercial shipping conglomerates will autonomously suspend their transit routes to avoid financial ruin, effectively shutting down the shipping lane without the defending force firing a single conventional missile. The sea mine, therefore, operates as an invisible, decentralized blockade. To truly understand the mechanical brilliance behind this strategy, we must first examine the extreme physical parameters of the operating environment. The ocean is arguably the most hostile engineering environment on the planet. Any piece of machinery deployed beneath the waves is immediately subjected to a relentless barrage of physical and chemical attacks. First, there is the issue of galvanic corrosion. Saltwater is a highly conductive electrolyte. The moment you submerge a ferrous metal casing, the electrochemical oxidation process begins, relentlessly eating away at the structural integrity of the metal. Second, there is the challenge of hydrostatic pressure. For every 10 meters you descend into the water column, the pressure increases by exactly 1 atmosphere. A mechanical device anchored at a depth of 50 meters must constantly withstand a crushing force trying to implode its internal circuitry. Third, and perhaps most complex, is the acoustic and magnetic clutter of the ocean floor. A busy shipping strait is not a silent void, it is a chaotic symphony of background noise. You have the constant churning of commercial propellers, the cavitation bubbles from passing tankers, the shifting of tectonic fault lines, and even the biological acoustic signatures of marine life. Therefore, the core engineering challenge of manufacturing these 6,000 devices is not simply creating an explosion. The challenge is creating a state of suspended mechanical animation. How do you engineer a cheap, mass-produced sensor module that can sleep in the freezing, crushing, highly corrosive darkness of the seabed for months or even years without its battery leaking or its circuits shorting out? Furthermore, how do you program its primitive electronic brain to filter out the thousands of false signals in the water, remaining completely dormant until the exact moment a specific magnetic anomaly or acoustic frequency passes overhead? At which point, it must wake up and trigger a detonation sequence in less than 1/1000th of a second. This is the extreme engineering reality of the Maham and EM series sea mines. To understand how they accomplish this impossible task, we have to look inside the production line and dissect the core mechanical modules that make this asymmetric nightmare a reality. When we rip open the mechanical anatomy of this asymmetric arsenal, we find a highly diversified portfolio of destruction. The strategy does not rely on a single, easily countered device, but rather a layered, multi-tier defense network consisting of three distinct engineering architectures: the Maham 3, the Maham 7, and the EM52. The Maham 3 represents the backbone of the moored mine inventory. At first glance, its spherical, spiked casing looks like a relic from the 20th century, but internally, it is a marvel of resilient engineering. The unit consists of a heavy anchor base, a high-tensile steel wire tether, and a positively buoyant explosive sphere. The true engineering brilliance lies in its dual-sensor logic gates. In the past, moored mines relied on physical contact. The Maham 3 relies on influence. Embedded within the casing is a highly sensitive magnetic anomaly detector, or MAD, coupled with an acoustic hydrophone. When a multi-ton steel hull displaces water overhead, it creates a massive localized distortion in the Earth's natural magnetic field. Simultaneously, the ship's massive bronze propellers generate a distinct frequency of acoustic cavitation bubbles. The Maham 3's rudimentary logic board is programmed to cross-reference these two data streams. If the magnetic flux and the acoustic frequency perfectly match the predefined signature of a commercial tanker or a military destroyer, the circuit closes, firing the detonator. It is cold, mechanical, and infinitely patient. However, moored mines can be detected by specialized mine-hunting sonars. To counter this, the network utilizes the Maham 7, a bottom-dwelling stealth munition. Unlike the spherical Maham 3, the Maham 7 is geometrically designed to sit flat on the seabed. Its outer casing is constructed not from standard steel, but from specialized composite materials coated in anechoic rubber. This material acts as an acoustic sponge, designed to absorb and scatter the active high-frequency sonar pings emitted by naval minesweepers, effectively rendering the device invisible to standard acoustic sweeps. Because it sits on the bottom, it cannot rely purely on magnetic sensors. Instead, the Maham 7 utilizes a hydrodynamic pressure sensor. When a 300-meter-long supertanker displaces hundreds of thousands of tons of water as it moves, it creates a massive, localized drop in water pressure, a phenomenon governed by Bernoulli's principle. The Maham 7's micro-diaphragm detects this microscopic shift in the water column's weight, triggering the explosive payload directly upward to crack the ship's keel. Finally, we have the EM52, the most mechanically complex system in the inventory. This is not a static explosive. It is an encapsulated, vertically launched rocket mine. Positioned deep on the ocean floor, far below the draft of any ship, the EM52 lies dormant inside a watertight launching silo. It relies on a passive sonar array to track the acoustic signature of incoming targets. Once the internal processor calculates the target's trajectory and speed, it does not detonate in place. Instead, it ignites a solid-state rocket propellant. Igniting a rocket motor underwater is an extreme thermodynamic challenge. The initial blast must forcefully eject the watertight cap, allowing the high-velocity rocket to punch through the dense water column at supersonic speeds. The kinetic energy alone is enough to shatter structural ribs, but the warhead ensures complete penetration of double-hulled vessels. How do you manufacture these highly specific mechanical systems on a mass scale, pushing the inventory to 6,000 units while driving the unit cost down to the $50 margin? You rely on the brutal, unrelenting efficiency of heavy industrial metallurgy. The production line begins in massive, centralized foundries. Here, the casings for the Maham series are not precision machined, they are mass cast. Molten steel alloy is poured into thousands of sand molds simultaneously. Once cooled, automated robotic arms, the few pieces of high-tech machinery on the factory floor, are utilized to rapidly arc weld the mooring lugs and sensor housings. The goal is not aerospace-grade aesthetics. The goal is raw, functional durability against hydrostatic pressure. The most critical and dangerous phase is the explosive filling. You cannot simply pour raw TNT or RDX into the casing. If even a microscopic air bubble is trapped inside the explosive matrix, the crushing hydrostatic pressure of the deep ocean could compress that void. The resulting friction from the collapsing bubble would generate enough heat to cause a premature detonation, destroying the deploying vessel. To prevent this, the explosive compound is heated to a highly specific viscosity and injected into the mine casings under intense hydraulic pressure, utilizing heavy industrial presses that exert forces equivalent to the weight of a small building. This ensures a completely dense, void-free kinetic core. Finally, the electronic brains are installed. To survive the highly corrosive saltwater environment, the printed circuit boards are heavily coated in epoxy resins, and the sensor access points are sealed using heavy-duty, high-pressure synthetic rubber O-rings, compressed and locked into place by torque-controlled pneumatic wrenches. Every single unit rolling off this assembly line is a perfectly sealed, pressure-resistant capsule of destruction, ready to be pushed into the logistics chain. Once the manufacturing line has pumped out thousands of perfectly sealed explosive spheres and composite bottom dwellers, the next monumental engineering hurdle is the physical logistics of deployment. How do you secretly inject a 6,000-unit mechanical network into one of the most heavily surveilled bodies of water on Earth? If a state actor utilizes a dedicated heavy-tonnage naval mine layer, military satellites equipped with synthetic aperture radar will instantly track its wake, calculate its trajectory, and perfectly map the drop zones. Therefore, the tactical engineering doctrine dictates the complete elimination of conventional military vessels from the deployment equation. Instead, the deployment mechanism relies on stealth through acoustic and electromagnetic noise. The network utilizes a massive, chaotic fleet of civilian wooden fishing dhows and low-profile composite speedboats. From an electromagnetic perspective, wood and fiberglass possess an incredibly low radar cross-section, rendering them virtually invisible to high-altitude radar sweeps. To the algorithm of a surveillance satellite, they are simply local fishermen casting nets. However, deploying a heavy mechanical payload from a small, unstable platform introduces extreme physical risks. You are taking a steel sphere weighing several hundred kilograms and pushing it into a turbulent, fast-moving ocean current. The hydrodynamic drag alone is immense. If the heavy anchor base and the buoyant explosive sphere become entangled during the freefall, the high-tensile steel tether could snap. Even worse, the sudden kinetic jerk could prematurely activate the internal sensors, detonating the mine directly beneath the deploying speedboat. To solve this, the engineers utilize a purely chemical safety mechanism, the water-soluble plug. When the mine is rolled off the deck of a fishing boat, its electrical circuitry is physically broken by a hardened block of sal, ammoniac, or compressed sugar. The mine is effectively completely dead, lacking any electrical current, while it sinks and crashes violently into the seabed. It is only after several hours of submersion, as the salt water slowly dissolves the chemical plug, that the galvanic switch closes, arming the internal logic board. This simple chemical delay allows a disorganized fleet of civilian boats to blindly dump thousands of mines into fast-moving currents with absolute zero risk of self-detonation. Once the minefield is chemically armed, the mathematical nightmare for the opposing navy begins. We enter the phase of inverse asymmetric attrition. To clear a shipping lane, a modern navy cannot rely on visual inspection. They must deploy autonomous underwater vehicles, or AUVs, equipped with ultra-high-resolution side-scan sonars and magnetic anomaly detectors. But remember the Maham 7, coated in anechoic rubber. When the multi-million-dollar AUV emits a high-frequency acoustic ping, the rubber matrix of the mine absorbs the sound wave, converting the acoustic energy into microscopic amounts of heat. The sonar screen simply registers a blank void, indistinguishable from a submerged rock or natural seabed topography. To confirm the target, navies must often send in remote-operated vehicles equipped with high-definition cameras or deploy highly vulnerable human explosive ordnance disposal divers. This creates an unsustainable logistical bottleneck. A modern maritime force is forced to utilize a $10 million robotics platform backed by a $1 billion coastal combat ship, consuming thousands of gallons of aviation fuel and diesel every hour, just to locate and neutralize a single $50 iron casting. The time and capital required to clear just 1 square kilometer of ocean makes rapid military advancement mathematically impossible. But the ultimate brilliance of this mega project is that the physical destruction of the enemy hull is entirely secondary. The true payload of this 6,000-unit arsenal is not the RDX explosive. It is the economic paralysis of the global infrastructure. The deploying force does not need to sink a fleet of warships to win the engagement. They only need to wait for a single commercial crude oil tanker to trigger a magnetic sensor. The moment that first massive detonation is confirmed, shattering a vessel's hull, the global maritime infrastructure automatically self-corrects. Major underwriters in London will immediately categorize the entire strait as an active war zone. War risk insurance premiums will instantly skyrocket by 400 to 500% per voyage. The profit margins for shipping conglomerates evaporate overnight. Consequently, automated logistics algorithms will halt all shipping traffic. The fleets of 300-meter-long supertankers will drop anchor and refuse to enter the strait. In a matter of hours, 20% of the global liquid hydrocarbon supply chain is completely frozen. Refineries on the other side of the planet shut down, global energy markets destabilize, and the entire industrial economy feels the shockwave. This is the terrifying beauty of heavy engineering utilized for asymmetric warfare. It proves that you do not need the most advanced silicon chips or the largest defense budget to control the world's most critical infrastructure. You only need to understand the physical limits of the ocean, the basic principles of mechanical sensors, and the absolute power of mass production. A $50 iron sphere, engineered with ruthless efficiency, can bring a $1 trillion global economy to a grinding halt. If you are fascinated by the extreme mechanical engineering behind global megaprojects and the silent machines that control our world, make sure to hit the subscribe button and turn on notifications. We dissect the heavy machinery of the modern era, one blueprint at a time.